How you doing? I'm Mr. Rose, and today we're going to talk more about kinetic energy in the form of translational and rotational kinetic energy. We're going to only do one problem. This problem is going to have a little bit of a sidebar to it. The question we're talking about today, as you can see, is I'm going to try and calculate the kinetic energy of the Earth as it orbits around the Sun. So to do that, first of all, you can see some gross approximations that we're going to make. I'm going to assume that the Sun is that the Earth is a completely circular orbit. We're going to assume that all the center of mass between the Earth and the Sun system is located at the Sun, and we're going to make an assumption that the Earth is a uniform sphere. Now you can also see that I wrote down some important information we're going to need. Here I have the radius of the Earth to the Sun, 1.5 times 10 to the 11th meters. Here I have the mass of the Earth, 5.98 times 10 to the 24th kilograms. And last, the radius of the Earth of 6.38 times 10 to the 6th meters. Now, as always, I do suggest that you try this problem before you just watch me solve it. Then keep going frontwards and backwards, seeing how we did. Some things to note. As we do this problem, you're going to need to be able to calculate or understand a couple of different things. As the Earth is rotating into that circular orbit, there are two things going on that we're going to talk about. As the Earth is traveling in that orbit, for example, the speed at which it is rotating on the outside, that is our translational speed. So that will indicate, I didn't want to use the word translate there. That will move to the translational kinetic energy, or kinetic energy as we know and love, 1/2 mv squared. The Earth is also spinning, and thus that also has some kinetic energy, and that's going to be our rotational kinetic energy. So the next thing I'm going to point out, the sidebar that we're going to take, I know I'm going to find the kinetic energy is the translational kinetic energy plus that rotational kinetic energy of the Earth. And I know that this kinetic energy total, I guess I'll write total there, is 1/2 the mass of the Earth, v squared, plus 1/2 I omega squared. Now the sidebar we're going to take is that I. Normally you can look up I, or the moment of inertia, for a uniform sphere, 2/5 mr squared. We're going to take time to actually go through and calculate that in this video. So it might be a little long, but I do think it's valuable for you to see. Again, at this point, if you want, I would recommend trying that yourself. Here's the hint when you calculate the moment of inertia for I, and the moment of inertia for the sphere. Well, the sphere is a three-dimensional object. That's actually a little difficult. Normally, we will calculate the moment of inertia for rods or thin disks, things like that. So what I'm going to do is I'm going to take the moment of inertia of a disk and extrapolate that out into the moment of inertia for the sphere. So that's my plan, just in case you want to try and go ahead. I'm going to first deal with this 1/2 mv squared because that part is super straightforward. So my translational kinetic energy is going to be just 1/2 the mass of the Earth times the velocity of the Earth going around that circle squared. Well, how do I get that velocity of the Earth? The velocity of the Earth, we know, is traveling in this nice little circular orbit. A pretty good circle. So if I have a tangential velocity that I'll call velocity v, I can solve that because I know the distance around my circle is 2 pi r, or the circumference, and then I know the time. So I know velocity is distance divided by time, which is 2 pi r divided by t. Well, what is the time it takes to make one complete orbit around the Earth? The time it takes to make one complete orbit is 365.25. We need to change days into seconds eventually, so that is 24 hours in a day, and then there are 3,600 seconds in 24 hours. If I take that and multiply that through, I have a time of 3.156 times 10 to the 7th seconds. So now my kinetic energy, the translational kinetic energy, 1 calculator error. I got my translational kinetic energy to be 4.28 times 10, I'm sorry, 82. 4.82 times 10 to the 24th. And that'll be a joule. So that is not my total, remember, that is my, oh, I'm off the screen, I'm sorry. That is my translational kinetic energy. So now we're going to focus on this much more difficult part, the 1/2 I omega squared part. So again, now we're going to work with this kinetic energy part, 1/2 I omega squared. And as I said, I'm going to attempt to calculate out that I. So we have a sphere. This is going to be a terrible drawing. It's already not good. There we go. We're going to have a sphere, and that sphere, right, that dotted line means it's a sphere. That sphere is going to have this disk. Now that is supposed to be, that's not bad. That is supposed to be a slice, a disk that is just at some arbitrary spot in my sphere, right? I know it's going to take a lot of disks. I can start here, a disk, a disk, a disk, to make up that entire three-dimensional sphere. And that's what I'm going to start to work with, right? So we know that, let's see, I need to, guess I'm going to define my radius of the disk. And I'm going to say my sphere has the sphere has a radius big R. We're going to need that a little bit later. And I know that this little r, the radius of my disk, is going to be dependent on where it is about my axis, like my x-axis. A disk here, for example, will be much smaller than this blue disk that I drew in the middle. So how am I going to try and find out or calculate the moment of inertia of that sphere? That is what I'm going to start to work with now. So essentially, I already kind of hinted it to you that we're going to add all of these little disks up, which means I'm going to have small moments of inertia. Now, that means I know, let's see, I know I is equal to 1/2 mr squared. That's the I for a disk, right? So I disk 1/2 mr squared. Well, if I have a small one and lots of them, that means I could have like a di, a differential moment of inertia, equal to 1/2. I'm just going to move this and put the r squared there. And now I'm going to call this a dm. Well, again, we know that we see this di, this dm. We're going to start talking about integration or summing all of them up. But r is a function of x, not a function of mass. So we're going to start to need some kind of relationship. So again, I'm going to use my cheat. I'm going to say rho, that is my density, is a small differential mass unit divided by a differential volume. And I know that because we also know that density just by itself is mass per unit volume, right? So I'm just changing back and forth. A small piece is density, a large piece, same density, especially because we're assuming the Earth is a uniform sphere, which means I'm not going to use this right away, but I'm just going to say that rho, or the density of the sphere, is mass divided by 4/3 pi r cubed. That is the density, big R, because I said big R was the radius of my sphere. That is the density of my entire sphere. So now looking at this relationship that I circled, rho is dm dv, that means I know dm is equal to simple math, rho, right? So now I can substitute in here. I'm going to say my differential moment of inertia, di, is equal to 1/2 r squared times rho. All right, well now how is this helpful? Well, remember now I'm thinking about this disk. I'm not actually thinking about the sphere anymore, just the disk. The volume of the disk, or, you know, this, there we go, this like very small cylinder, almost solid, is the volume, I'm going to say dV, is equal to what is that? That's kind of like a circle. So I'm going to have a 2, do I want a 2 pi? No, not, I don't want a 2 pi. Circle, pi r squared. Get with it, Rose. Pi r squared. That gets me the area times my thickness, right? Times dx. Now, dx is arbitrary. Again, I don't have an axis drawn here, but if I put an axis in the middle, and I can extrapolate that into my x-axis, which means, just like I stated earlier, if I move these disks all the way across my x-axis, r is going to change, so they're dependent. So now I have di equal 1/2 r squared, rho is still rho. dv, I'm just having a direct substitution here. I'm going to say pi r squared. And now again, I've hinted at this already. R and x are dependent on each other. My radius r is different if it's here to here. So I'm still not done yet. I essentially need to make those two guys work together, right? Because r kind of looks like it's a constant here and it's not. So I'm going to redraw a kind of a simplified diagram here. Randomly change my handwriting there, that's great. So they depend on each other, so I need to make them play together. So now I'm going to, again, I'm taking this axis and simplifying it. Now I'm going to not be able to draw a three-dimensional disk, so we're going to have to use our imagination. That is my three-dimensional disk. This represents part of my sphere. Any disk that's making up that sphere. Again, I know it's not the best. And I'm imagining that as, again, maybe I need to draw that, imagining that as part of that big sphere, where this is the three-dimensional radius of my sphere. That disk that I drew is some arbitrary distance x away, and just so we can see it, that is my lowercase r. That is the radius of my disk. And hopefully we see, holy cow, that looks like a right triangle, which means I have, let's see, x squared plus, I guess I'll keep my color, r squared equals big R squared, Pythagorean theorem, which means I've got an r here. Hey, and look at that, I've got an r there. And then I can get things in terms of x, where this radius, big R, radius of my sphere, doesn't change. That becomes a constant. So now I'm going to say di is equal to 1/2. I'm going to keep my rho. R to the 4th, that's just going to be, let's see, I'd say r squared is equal to big R squared minus x squared. So r to the 4th would be that squared, I believe, right? So I'm going to say that is big R minus x. Oh, I need those squared. That whole thing is squared dx. Looking if I did that right. Yeah, that's right. I like it. Okay, so now I can start, look, constant. Oh, I dropped the pi. Pi is a constant. I just don't want to exclude it. So now I can see constant dx. I can start to realize that when I take the antiderivative, I can pull out these constants. I'm going to have an x here. I am going to simplify it first. I'm going to say, well, I'm going to stop writing this di. I know eventually I'm going to integrate both sides. So I'm going to say I is equal to, actually, you know, I'm going to go to a new page. There we go. So that's where I was going next. And from there, I'm going to say that I'm going to integrate. So I have I is equal to, right, take the antiderivative of that side. And eventually I'm going to take the antiderivative of that side, but I want to simplify that first. So the antiderivative of 1/2 times rho times pi times, all right, I'm going to not do that in my head. That is, now I can do that in my head. Antiderivative 1/2 times rho times pi times plus x to the 4th dx. Whew. All right, that looks ugly, but it's actually really, really, really nice. This is going to be super easy. Now I'm going to say, pull out my constants. X. Go back to my picture over here. Now my limits of integration. I put this sucker right in the middle kind of intentionally. I'm going to integrate from negative r to r, but it's perfectly symmetrical. I don't want to integrate from negative r to r. Choose your limits of integration, what you're going to sum up intelligently. I'm going to use for the limits of integration 0 to r. So I'm going to define this as 0 and go from 0 all the way to the radius of my sphere, big R. And then when I'm done, I can double it because perfectly symmetrical. So my limits of integration here, I'm going to add this into color, 0 to r, and I'm throwing in a number 2 there. That number 2 is because I'm going to go from 0 to r and double my answer. If I do it this way, my integration is going to be so much easier. So now I have I equals, well, 2 1/2, that obviously is going to go away. So now I have rho times pi times, first I'm going to integrate r to the 4th dx from 0 to r. That's going to be an r to the 5th minus, oh, you know what? Let me not skip that because you may not be there. I'm going to say from 0 to r. And now, as you saw, this is where it's easy to come from. Plug r into there. That's going to be r to the 5th minus x cubed is going to be r cubed. That's going to be 2/3 r to the 5th plus r to the 5th over 5. That 0 is going to be minus all those 0 terms. So now my moment of inertia is my moment of inertia. That does not look like any moments of inertia we've ever had. So what do I do here? Well, first thing I'm going to do is, I know I can use a calculator, but I'm not going to. I'm going to add these. So I'm going to find a common denominator. My common denominator looks like it's going to be 15. So I'm going to say my moment of inertia is equal to 5, that's 6, 7, 8. That means I is equal to rho times pi times 8 r to the 5th over 15. Woo! Man, 23 minutes in, we're still not there, but we are close. Let's recall we defined rho way long ago. We're talking about a sphere, the density of a sphere, mass per unit volume. And I'm going to clean that up a little bit. I'm going to make that look a little bit better, just because it's going to be easier to plug into that. I'm going to say rho is equal to, flip. Now I'm going to plug that directly in. I equals. Hopeful you see finally where this is going. My pi's cancel. 3 into 3 goes once. 3 into 15 goes 5 times. 4 into 4 goes once. 2, third, that goes to a second. That means my moment of inertia about a uniform sphere. I could have looked it up on page 294, I think it is, in the textbook that we use in class. But the moment of inertia is 2/5 pi r squared. Man, that was a long way for that. Don't forget, this is not actually the purpose of our problem. We need to use that in my kinetic energy. So, just proved that. I'm finally going to go back now into my kinetic energy is equal to K translational plus K rotational. We already got K translational. K is equal to 4.82 times 10 to the 24th. I thought maybe I can cancel out a mass of the Earth, but I can't. Plus, let's see, that is going to be 2/10, right? 1 times 2 is 2. 2 times 5 is 10. So it's actually still going to be a 2, right? 2/10, which is going to be a 1/5. 2/10, 2 over, yeah, 1/5 mass of the Earth. I wrote down before, 5.98 times 10 to the 24th kilograms. times radius of the Earth, 6.38. 6.38 times 10 to the 6th meters. That is 1/2 I. That's got to be a squared. Times, oh man, what the heck? How am I getting this omega squared? Well, we've seen before where I could make a relationship between velocity, radius, and get omega, but here I'm not going to do that. I'm going to actually calculate omega squared. It's not that going to be difficult. Omega is equal to, well, at 1 revolution, 2 pi, divided by, well, it spins once in a day, 24 hours in a day, 3,600 seconds. I'm going to slam that right into there. So now I have a K equal to this looks like it comes out to 2.57 times 10 to the 29th. I do think I made a mistake. I'm going to recalculate this whole thing. So let's see. Is 2.65. That sounds better. Kinetic energy of the Earth rotating around the sun is 2.65. 2.65 times 10 to the 33rd. 33rd joules. That was a long way to go. I hope you got something out of this. Please feel free to like, comment, and subscribe. Like I said, lots of things to do. We started with, there it is. We started with a sphere. We cut the sphere into a disk. We added all those disks up to figure out the moment of inertia about that disk. Used that moment of inertia to find the rotational kinetic energy. Added that to the translational kinetic energy to find the kinetic energy of the Earth rotating about the sun. Again, that's all I have for you. Please feel free to like, comment, and subscribe, and you will see me next time.